Good evening, everyone present here. Welcome to today's Kaapi with Curiosity talk. I also welcome the audience joining us online. So I request our director, Dr. B.R. Guruprasad, to formally welcome the gathering.
Good afternoon to all of you. Respected speakers, respected visitors, students, and the general public, ladies and gentlemen. Good afternoon once again to this very important and very exciting lecture on an exciting subject. What does not kill cancer can make it stronger, and investigating cancer as a complex system by Dr. Mohit Kumar Jolly, Associate Professor, Indian Institute of Science, Bioengineering. Welcome to you, sir. Thanks for this kind gesture. And this is, as you know very well, this is a joint program of International Center for Theoretical Sciences and ICTS and JNP. And once again, I welcome you all. And I don't want to take much of your time before Professor Mohit Kumar Jolly begins his lecture. But let me take this opportunity to announce a little bit about our summer programs at JNP. We have lots and lots of programs for students at different levels, okay, at JNP in the coming 2 months. For those very young students, we have Tiny Tots program, and Fun with Science is yet another program for about 5th to 7th grade students. And an exciting aero modeling workshop is also being organized. And one-day workshop for students for 7th and 8th grade is there. Astro computing is yet another program. Astronomy through apps, okay, this is another program. And summer course for high school students. This is yet another program which runs for quite a few days. And another important program is From Web of Life to Universe. Totally we have about 12 programs, and apart from whatever I announced just now, Zero Shadow Day workshop is yet another one. Universe in the Classroom, Explore. And apart from this, not only for students, we have an exciting program pertaining to training teachers. So in the next 2 months, we are very busy at JNP for non-formal science education as well as for science popularization. Coming back to Kaapi with Curiosity today, once again, I thank Professor Mohit Kumar Jolly for this kind gesture, and I would like to okay, now I will invite, okay, you announce. Okay, fine then, please.
I request Dr. Akshit Goel from ICTS to introduce the speaker.
Hi, it's nice to see such a nice turnout for this event today. So today we have Mohit Kumar Jolly from the Bioengineering Department at IISc, sort of speaking to us about cancer as a complex system. Sort of briefly about Mohit, he did his bachelor's and master's degree from IIT Kanpur, after which he moved to Rice University to do his PhD in bioengineering, and after which he sort of stayed on as a postdoc jointly with the UTMD Anderson Cancer Center, where he worked with Professor Herbert Levine and Professor Samir Hanash on sort of various aspects of cancer and sort of modeling it, and that's also what his lab at IISc does now. Mohit's work is sort of very interesting because, usually we think about cancer as, a bunch of molecules, this extremely medical thing, extremely biological thing, and it is. Sort of Mohit's work takes this sort of nice approach of thinking about the mathematics and thinking about cancer as a population of different kinds of cells within our bodies that are interacting with each other. And Mohit's research over the many years has shown that it's actually very useful, not only fun to sort of think about sort of cancer in this way, and I'm sure we'll see glimpses of that in his talk today as well. So with that, I won't take much more time and invite Mohit to come and speak. Before he speaks, I'd like to quickly give him a token of gesture on behalf of ICTS. And over to you, Mohit.
Thank you, Akshit, for that very kind introduction, and thank you, ICTS. Thank you, Jawaharlal Nehru Planetarium. The outreach teams have been very kind to invite me. It's my real pleasure to be doing this and sharing some of my journey, and I have also been interested in science communication more as a hobby. At some point I thought of it as a career, but here I am. So I would really like to get feedback, make it as conversational as possible. Anytime there are any questions, any clarifications, please do stop me, and we'll take it from there. So before I begin and start to talking in more detail about what we do and how we think about cancer as a complex systems and some of the approaches that have been used by people studying different complex systems, be it weather prediction, be it outer space, be it financial markets, etc., how some of them can be used to think about cancer progression and potentially go to a stage where we can suggest better therapies as well into this. Okay. So this is the book I read 12 years ago. It was a popular science book that came out, which of course later won the Pulitzer Prize, Cancer, the Emperor of All Maladies, and it had such an impact on me that I decided to work in cancer biology for my PhD, postdoc, and later. So that's the importance of public communication of science and popular science here. As it clearly says, cancer, this word, when we hear, it sends a shiver down our spine because we still know very little about this disease. I mean, compare it to different cardiovascular diseases where we have made tremendous progress in terms of, cutting the risk down, in terms of also interventions, but cancer still, as I'll talk about, some of the therapies are still more than 100 years old, at least in their foundational concepts, and really have not evolved with time per se. So what is cancer? Cancer is a group of diseases where the basic property is that the cells start growing in an uncontrolled manner. So every cell in our body, we are made of almost 10 to the power 14 cells, and every cell in our body has an internal clock. It knows how many times to divide, and then it no longer divides, right? And that is what keeps the structure of different organs and function of different organs intact. Who gives that clock? How is that clock different from one organ to another, etc.? Those are, of course, beautiful questions, but I'm not going to delve into that today. But this is one of the major aspects. And the second thing I've highlighted here is that cancer has this unique ability to spread to different parts of the body. You think about most other diseases, they remain restricted to the organ that they originate in. They don't keep moving around and forming their horcruxes in different parts of the body, which eventually leads to multiple organ failure, and that is why cancer patients eventually die without being cured of it. So this is an example. This is image of a liver, and what you see here in speckles, these are pancreatic cancer cells who have found their way in a liver. And as you can clearly see, approximately half the area of this organ is now infested with these cancer cells, which eventually disrupts the function of this particular organ and many other organs that cancer cells have the ability to metastasize to. Metastasis is the process through which cancer cells go from one organ to another, and that's why multiple organ failure is why most cancer patients die. These are just some statistics, so how the number of the incidence of cancers looks like. So this is the data from the US. As you can see, irrespective of the age bracket that you look, the number of cases are only going up. And this is the data from India. It was published last year, saying that in 2025, we are expecting somewhere around 15.7 lakh cases all over the country. Now, as compared to the US, these numbers may look small, but I'll show you another data, which is how many patients die of cancer. In the US, despite large numbers, the approximate number of people dying of cancer every year over the past 30 years is more or less around 6 lakhs. In India, that's already more than that. Almost 10 lakh patients are dying in India, and this is from 5 years ago, so of course numbers have gone up much faster, right? So why are more patients dying in India relative to, if you think about the percentage of incidence? There are multiple reasons. We perhaps get diagnosed later. Some of the cancers that we are getting, and there is some data for this, are the ones which are more aggressive as compared to the ones that you see in the US. So the distribution of different organ types is not exactly the same. So there are multiple reasons behind this. But just some statistics: in the US, for instance, 1 in 3 women and 1 in 2 men have the risk of developing cancer in their lifetime. In India, that number is already 1 in 9. We are not that far. Okay, we are not much far away from the numbers that we are already seeing here. Okay, so clearly we need to understand this disease better. We need to manage this disease better. We need to treat this disease better. Okay. Now, what are the current strategies that are used for treating cancer? So one is, of course, surgery. Surgery has been used for a long period of time. This is just one example I'm showing here. This is called radical mastectomy. What this means is that for women who had breast cancer, their entire one or both breasts were removed. That used to be the way this particular disease was treated about almost in the early 1900s as well. And William Halsted is one surgeon who sort of perfected this technique, which continued to be used for a long period of time. Around the turn of the century, when X-rays were identified, people started using it to treat for cancer. And around the World War II, mustard compounds were identified that they could actually kill cells, so that then eventually evolved into the use of chemotherapy. Move 40 years later, 1980s, so these, as you can see, are very generic therapies, right? Either you remove the complete organ or you target every cell of the body in a given area. So how radiation and chemotherapy works is by damaging the DNA. Okay, there's no specificity which cell exactly it will go and bind to. And that is where targeted therapy comes in, which basically means that instead of shining radiation on an entire area of the organ, you actually have a molecule which will bind to specific cells, and we'll go into details of that. And those specific cells, being the cancer cells, will be the ones that will be eventually impacted. Okay, almost 3 decades later, immunotherapy is now the latest treatment that we have, and this got the Nobel Prize a couple of years ago. What the central concept behind immunotherapy is that you basically tweak the immune system of the body such that it becomes more effective in handling cancers, right? So we have the immune system, but somehow cancer is able to trick the immune system in not killing those cells. So how can we make the immune system more potent and more effective in identifying it as early as possible and then eventually eliminating it, is the central tenet behind this therapy. Of course, there are multiple details of it which I'm not going here into, but these are the general ideas, and this is how the evolution has happened in the past 130 years or so. Now, if we have such diverse treatment options, why we have not yet been able to cure cancer, right? So what are the different stages of cancer progression? So think about a tumor which gets initiated in one or more cells in a given organ, and then because this cell will grow much faster as compared to the other cell, you can see that it begins to disrupt the normal architecture of the organ, and then it begins to invade and eventually goes to other organs of the body called as secondary tumors. Now the time scale that you see here can be different for different tumors, but what I'm trying to emphasize is the acceleration in the process that happens once the tumor is out of where it initiated. Okay? Now in the past 60 to 70 years, we have made some fantastic progress in diagnosing cancer early. So now there are tests that both men and women can go for, at least for identifying the risk of prostate cancer and breast cancer. We have made progress in identifying which genes are involved, and therefore hopefully more effective targeted therapies can come in. We have identified risk factors such as smoking causes lung cancer. But as you would see, all of these progress largely restricts themselves to the initial phases. We have not made any breakthroughs once cancer begins to leave the other organs, right? We have no therapy yet which specifically targets metastasis. All the therapies that we have are efficient in cutting down the primary tumor mass, but not beyond that, right? Now, and metastasis, that's why, still remains the cause for 90% or more of all cancer deaths. And this is just a schematic showing that cancer cells from one organ can go to multiple different organs in the body. How does it do that? It's largely through this fantastic set of freeways that we have in our body called the blood vessels. So the blood vessels are of course spread all across the different organs in the body. So imagine a cancer cell sort of crawling in, getting in the bloodstream, and then spreading to different parts of the body, taking exit at different organs and eventually forming metastasis. Now, the most striking thing to me was when I started reading this literature was that if you think about solid tumors means everything except blood cancer, okay? Breast cancer, prostate cancer, lung cancer, liver cancer, etc. They are all so-called epithelial organs, which means that cells do not have the property to move, right? Cells in prostate stay there. They are born there, they die there. They don't have the ability to start moving randomly. So then how do cancer cells get this ability or acquire this ability that they can leave a particular organ, settle in a completely different organ, and also eventually colonize that organ so much that you disrupt the functioning of that organ? It's not just some normal growth that these cells are able to do. They're able to divide at such a rate that you eventually disrupt the other organ, right? So what are those properties? How do cancer cells gain these properties? And what are the challenges in developing anti-metastatic drugs? Okay, so let me give this analogy. How many of you have seen Harry Potter? Okay, so you realize this is the first scene of the first movie, and well, close to the first scene of the first movie, and this is close to the last scene of the last movie, right? If I give you only these two pictures and ask you, someone who has not seen the movie, tell me what happened in between. Anyone who has not seen the picture wants to take a guess? Anyone who has seen the picture, the entire lecture will be gone, so I don't in answering this question, right? So what I'm trying to say is that if you have only time point 1 and time point 2, which are very, very far apart from each other, and no data in between, how will you get to know what's happening in between, right? The same with metastasis. Patients come, get treated with some drug or surgery or chemotherapy, go back home, a few years, months, weeks, depending on which cancer we are talking about, they have metastasis. How do they identify it? Using some symptoms, right? And they come to the doctor again, and a biopsy is done, and they see there is a cancer in another organ. So when we don't understand the dynamics of a process, how can we develop drugs against that process, right? So the dynamics is very poorly understood. First of all, why do cancer cells leave the primary tumor? They're happily sitting there, getting whatever they need. Cancer cells have the unique ability to grow their own blood vessels also. They can, literally, as many people would cut into the electric lines to get power, they can do the same thing for blood vessels. They are able to do that. Then why do they leave? How do they leave? When do they leave, right? Do they leave as single cells or do they leave as cluster? Does it matter whether they leave as single cells or cluster? Which organs do they stop by? So imagine a cancer cell which leaves, say, prostate. Does it go equally to all other organs of the body? Or does it depend on which blood vessel it entered, or which lymph node system it entered, etc., etc.? And how much time it takes for them to grow a clinically discernible metastasis, right? Is it always years? Is it weeks, etc.? None of these questions are very well understood. Of course, there is some research being done here using different model systems that we have in the laboratory, but you don't have the answers of these, such as F is equal to MA. There are no laws for this. There is no clarity as far as that extent is concerned. Okay? The another unsolved challenge in cancer treatment, which I briefly referred to, is something called as tumor relapse. Tumor comes back, right? So here is an example. This is a melanoma patient. Melanoma is a type of skin cancer. This is pre-treatment. You can see all these lesions here, and then you give a particular drug. The patient is cleared of the lesion, and you continue the drug. In presence of the drug, 2 months after this, cancer is back again. Okay. Why this happens? Because this drug, it was not able to get rid of every single cancer cell. There were some cancer cells which are not so large in number that you would see a clinical outcome of it, but there were still some of them sitting there, and they have gained the ability to grow in presence of drug. They are supposed to be killed by the drug, but they somehow lay dormant and then again start growing. Okay. So again, we don't understand the dynamics of this as well, right? So whether this particular pre-treatment population of cancer cells, did it already have those cells which could hide or play hide and seek with the drug and then later come out? Or was this a new feature which was introduced due to the drug? Right? Unless you have dynamic data, you can't really say this. And can we delay this process? Can we push this process? Instead of 23 weeks, can this be 23 years? Right? Because that's where we are talking about extending the lifespan of patients. There are cancers in which if you extend the lifespan of a patient by 1 month, the drug is approved by the FDA, irrespective of what the quality of life is. Okay, so there are some cancers which are that aggressive, right? So let's think about this dynamics that I've been talking about in a little bit more quantitative, and this is what I would really want to, I have some questions and let's see what all you think about. So the first question is, let's say 10 to the power 4 cancer cells, 10,000 cancer cells leave a primary tumor. How many of them will complete metastasis? Any guesses? Out of 10,000 cells which leave, how many of them will complete metastasis? 1%, 10%? How many of you think it's more than 10%? More than 10%, okay. So more than 100, sorry, whatever, yeah, 1,000 cells, more than 1,000 cells will do this. How many of you think it's between 1 to 10%? Okay. Between 0.1 to 1%. Less than 0.1%. Less than 0.01%. So 1 out of 10 to the power 4. So the answer is 1 to 2 in 10,000 cells. Metastasis is a highly, highly inefficient process. So many cells just die on the way. Okay. Now, how do we know this? Of course, there have been some experiments that have been done. These experiments have been done in mice, but nonetheless. So this was done almost 25 years ago, where they injected cells in the vein that goes to the liver, called the portal vein. And then they measured, after different durations, how many of them eventually formed tumors, and the answer is 0.02%. And the rate limiting step here is them not getting out of the tumor, not getting out of the circulatory system. They get out of the circulatory system reasonably well, they can't settle in the other organ. Or they grow, maybe do 2 or 4 cell divisions or 10 cell divisions and then disappear. Growing in a completely different organ is not an easy task, right? So then that is where the highest attrition is. So the process of metastasis is highly challenging, right? Think of a cancer cell which has left the primary tumor. In bloodstream, it is facing shear stress. It is facing immune system. It is facing all the different drugs that you are giving. The concentration of oxygen and nutrients is constantly changing, right? So it cannot have just one strategy, because one solution is not really going to overcome all these different challenges, which also happen to be a function of time. So think of someone who wants to go abroad and settle there, or I'm sure you know people who have gone in a completely different cultural system and excelled there. What traits does it take? This is very much like that. Adaptability, fantastic. Anything else? Survival instincts, okay. So this we are talking about humans, but if we bring these properties down to cells, what would these be? Ability to multiply, replicate, ability to adapt, right, in multiple different scenarios. And exactly, that's what Charles Darwin also said, right? It's not the strongest, it's not the most intelligent, it's the one that is most adaptable, that is able to survive change constantly and eventually grow there. Okay. Now then the next question comes, is every cancer cell equally likely to survive? How many of you say yes? No? None of the above? It has to be yes or no here, right? In this case, right? So why do you think it's no? Or how would you test this? What an experiment would you do to say whether this is yes or no? Okay. How fast they adapt. All right. Okay, that's a good strategy. But how would you say that whether cell A is more efficient or cell B is more efficient? That's a great point. How much they reproduce. So reproducibility, the ability to reproduce and proliferate is clearly an important point. So think of this. I'll give you a thought experiment. Okay. So let's say there is some challenging question paper that has been set, which is given to a class, and that class has some more intelligent people and some less intelligent people, some moderately intelligent people. So we are already starting with a heterogeneous distribution. Okay. And we say, well, let's say how many of the questions were answered, correctly answered, okay? And you grade that and say 70%. Fine. You repeat this experiment multiple times and the answer is sometimes 60%, sometimes 65%, depending on the exact distribution that you have, right? Exact intelligence frequency histogram, okay, in some sense. Now you do the other experiment. You segregate the class, let's say the class has 100 students. You put each of the 100 students in a separate room and give the same exam and ask, what is the distribution, what are those 100 numbers in terms of the percentage of questions correctly answered? How many of you think it will be very similar to the population behavior? The population behavior was relatively tight distribution with say mean around 60 to 65 and some variation. But when you segregate them, the more intelligent ones would do much better than the less intelligent ones. So you would have some cases in which say 90% of the questions are answered and many cases in which 10, 20, 50, whatever, right? It will be a much wider distribution than that case, right? This experiment, which I just told you, won the Nobel Prize. Just this experiment, okay? This was done in bacteria in 1940s. It was jointly designed by a biologist and a physicist, both of whom got the Nobel Prize, called Luria-Delbruck experiment. And then this experiment was repeated in cancer by Fiedler and Kripke, and the answer they got was that when you look at the entire class, so again what they did is they took cancer cells, put them in mice, a large population versus populations grown from a single cell, right? So again, in a large population, the distribution was more closer, but here as you can see, some cancer cells or some generations of cancer cells or some sub-generations of cancer cells were abysmal at forming metastasis and some are very efficient. Okay, so it was like a distribution of the class that we just talked about. So which clearly means that not everyone in the class is equally intelligent and not every cancer cell is equally able to metastasize. Okay. So what we have learned so far is that cancer cells are heterogeneous. They have different properties. Some of them are more, just as people have different properties, some are more grumpy, some are more cheerful, etc., etc. So there are these different properties, and the technical term for that is phenotypic heterogeneity. Okay. And also cancer cells can adapt. So a grumpy person can become cheerful and vice versa depending on the environment that you put them in, and this is what is called as phenotypic plasticity, the ability to change their behavior. Okay. So you have different types of people or different types of cancer cells, and also you can't really say this, this is the fate of a cancer cell because the behavior is a function of time. Then the next question comes is, do these traits of heterogeneity and plasticity drive drug resistance? Okay. If you put these properties together, is that sufficient to explain the clinical observations that we have? Okay. So let's look at dynamics of tumor relapse. So this is the patient case that I showed you, which was for melanoma. So this is an experiment done in mice, in a melanoma mice model. What you see here is that when the drug was given, for the first 15 days, the tumor volume, which is on the y-axis, continues to decrease. Then for the next 3 weeks or so, the tumor volume doesn't change. This is called minimal residual disease, MRD. So you get the clinical observation that the tumor is gone, but it's not actually gone because this value is not 0. Okay, so slightly above 0, but still not equal to 0. The word approximate, devil is in the details. Sachin scored 99 runs or 100 runs. Approximately a century nahi hota hai, right? It's either a century or not a century, right? And then eventually you see that the tumor starts to grow again. Okay. Now, what is happening here is that, of course, there are some cells which are not killed, and then these particular set of experimental colleagues looked at some different molecules and showed that some molecules went up, other molecules went down, etc. They did a more detailed analysis, but we'll not go into that part right away. The general idea here is that during this phase, some cancer cells are able to adapt and they're able to survive in presence of the drug. The drug has not yet gone, and they are changing what their cell state is. What do I mean by cell state? Is the levels of different molecules in a cell at that point of time. Because the levels of molecules can change, their function can change, and that's what you define as cell state, right? Water can exist in 3 states. How do you change liquid to water vapor? Right? Similarly, ice. Right? So you can change the external variables and push them from one state to another. None of the current therapy that we talked about accounts for cell state transitions. Okay, so let me explain that more in more detail. So let's say you profile your tumor through the latest technologies that we have right now, and you identify that in a given tumor there are 4 different cell types. Okay, and you know, say, the targeted therapy for each of the 4 types. You know, cell type A, this drug I'll give, it will be dead. Cell type B, cell type C, cell type D. Okay, that it's simple. Give the 4 drugs and the tumor should disappear. How many of you think this would happen? You are fortunate enough to have targeted therapy for each of the cell type. And when I say fortunate enough, it means that that's not the state of the art. We are not yet there as a community. But let's say you are there 10 years down the line. Do you think this will work? Why?
So more types you will have, the number of types of cells will increase.
Okay, so will increase. Why will it increase?
Because they are getting adapted. They know that you are developing more drugs, more types of drugs, so it'll get adapted, just like drug resistant bacteria.
So if I understand your point correctly, you're saying that there are 4 cell types at this time, but as a consequence of the drug there may be new cell types which may emerge. Okay, that's a fair argument.
So just like drug resistant bacteria, so you mentioned this MRD state. So say we give them all of these 4 drugs and we have them at MRD. During that time they may take up certain genes or might modify themselves in order to be resistant to these 4 drugs, and then they can mutate as such, because cancer cells mutate very fast.
Fine. So there can be some long-term changes. Mutation means long-term irreversible changes in the behavior of a cell, because it's happening in the DNA, which is then getting passed on across generations. Okay. Any other reasons? So the population can adapt. Okay. Fine. Let's break it down further. What is a cell doing? Okay, let's look at one population. Let's make the argument real simple. Okay, let's assume you have only one type of cancer cells, broadly speaking. There's some distribution, some variability, but broadly speaking, one type. Okay, you know the targeted therapy. Now, when you give a therapy to patients, do you keep varying the concentration? You know the concentration we are talking about, right? So what is the assumption you are making? That every cell in that population will respond identically to that concentration of the drug and die. You're making 2 assumptions, as if they're just dumb agents sitting there waiting for an external instruction to be given. Avada Kedavra, they die. Right? That's not how things happen. Right? It's still the same cell type, but there is some variability, right? So these are the different assumptions we are making. We are also assuming that no drug itself can push a red cell to become a blue cell. We talked about new cell states, but even these can switch back and forth, whose rate can be altered by the drug that we are talking about. Why cancer would have different cell types? We have so far talked about that they have different cell types. Why? Why do you think a population would have heterogeneity? Why do you have different kinds of people in this world? Advantage, right? There's some evolutionary advantage, there's some potential of cooperation that might go on. And again, in cellular behavior also it has been seen, and I mean, Akshit works extensively on this, he can tell you more about this, that cells, different cell types, even in bacteria, can cooperate with each other. Right? So they can achieve together. What do I mean by cooperate? When you put cell type A and cell type B together, what they achieve is much more than what just cell type A or just cell type B would have been able to achieve. Okay? So there is some emergent property that you see there. So basically what I'm trying to say is that all therapies we have so far, they assume that cancer is a static system. We do not consider the dynamic, adaptive and complex nature of it when we design with whatever therapies we have right now, and that is why inevitably you will have resistance irrespective of which therapy you do, because the concepts is such different, right? So then the question comes, can a mathematical model help? So of course an argument I get is, well, cancer is so complex. If you think mathematical models were useful, we would have solved it now. Right? So what do you need for a mathematical model to be useful? Do you think weather prediction is a reasonably accurate system? It's also a prediction of the mathematical model. We need to know the dynamics, we need to know the variables, we need to know the interactions, we need to continuously revise the model and match it with real data, which we don't have. Right? So if you do not have dynamic data, you can build as complicated models as you want, but what will you match it to? How will you calibrate your data? How will you match it to individual patients or even different cohorts? The drug that works for Caucasian patients sometimes does not work for other ethnic groups. Why? Because there are variables we have not considered. We broadly say, well, ethnicity, what does that mean? These are some other variables which we have, we have to pin down and then put in our model, right? But mathematical models in general have the capacity to take in different interactions, take in different variables and say, okay, given these interactions and these variables, these are the possible dynamics. Okay, and then they can also tell you, if you tweak parameter A, this is the output you are eventually going to have. If you tweak A and B simultaneously, this is how we are. So it tries to build up predictive tools provided you know the interactions. Okay. So can we develop a model to study metastasis and drug resistance? Let's say if you were to build a model, what would you do? Okay. Before that, let me take another quick poll. When did you guys think, this is a question again as individuals, when did you last develop a model, mathematical model? In past 1 week, how many of you developed a mathematical model in past 1 week? Okay, and I've written the word mental in bracket, I'll come to that in a minute. Okay, past 1 year. Okay, never. Okay, so people who say never, please tell me whether you have ever played any sports. Any sports? You have played cricket, badminton, pool, anything? This has nothing to do with math model. Mental math model. You see the, which way the ball is coming. You know which direction to hit. You know what speed to hit. You adjust your posture and hit the ball. That's not math model. It's a one-dimensional model, or in a three-dimensional world, but it's still a model, right? What about badminton? You are, what you are doing, you are making the trajectory in your head. You're not solving the parabolic equation there, but you're still having some there. And then you know how much your body can stretch, how much you have to move, how you need to hit. It's all mathematical models, right? How many of you drove here today? Any vehicle? So when you see only 30 seconds are left and you are making a mathematical model whether you will be able to cross the signal or not. What equation is that? Right? You decide whether you want to accelerate and how much you want to accelerate to make sure that you cross the signal before it turns red. Also a simple equation of motion, one-dimensional mathematical model, right? How many of you invest in stock markets? It's a mathematical model, right? You're saying, okay, this is how the company has done in past 5 years, this is how I'm going to divide my money and do this. These might be rudimentary models or whatever, but they are models. They are mental models you are making, right? How many of you are in school and solving these kinds of real models, right? Smooth inclined plane and okay, tell the rate at which it will come, right? So all of us are mathematical modelers. It's just that we don't explicitly realize it in multiple sense, right? So we all develop models to answer some or the other precise question, whether I'll be able to hit the ball in a given direction, whether this will be a 4, this will be a 6, whether I'll be able to cross the signal before it turns red, etc., etc. These are all, you're not writing it down, but you're all doing it, okay? So as long as you have a precise question, you can develop a mathematical model, as simple as that. So we started with this precise question. Can metastasis and drug resistance drive each other? Okay, and the reason for this was this clinical data which was coming, that 1/3 of women which were treated with this particular drug, that's a targeted therapy, so it binds to one particular molecule, I'll come to that in a minute. So these women were treated with tamoxifen for 5 years and they had recurrent disease within 15 years and a majority of them were metastatic. And then there is more detailed clinical data showing that, never mind, but there is some graph which is not showing up, but basically that said that the longer the duration since the therapy has stopped, the higher the risk of getting metastatic cancer. So we were intrigued that on one hand we are seeing the property of drug resistance, which is tumor relapse, because the tumor is coming back after treatment. On the other hand, we see that this tumor comes back in a different organ. Why not the same organ? So it is possible that these two processes are coupled, that when cells are beginning to metastasize, they may have the property of drug resistance, and or when you make the cells drug resistance due to the treatment itself, you add the property of metastasis. These were the hypotheses we started with, okay. Now just to introduce the system, what is the system? So breast cancer, the way it is clinically characterized is based on these 3 molecules called estrogen receptor, progesterone receptor and some other receptor. These are all molecules present on the surface of a cell, okay. So when a pathology slides comes in, one would sit down and see whether these molecules are present in different parts of that slide or not, and then it gets characterized into these 4 cases, and that dictates the treatment, which drug will be given and so on, okay. So that initial categorization, just like sorting into the 4 houses of of a Harry Potter scenario, dictates what your outcome is going to be. So that sorting is crucial. And then this particular drug, tamoxifen, it binds to this molecule called estrogen receptor, which is actually the most frequent scenario of breast cancer cases. Now as compared to a normal breast cell, in a cancerous breast cell, the amount of this receptor present on the surface is much higher, and that is why the drug has the maximum impact on the cancer cell and it largely spares the normal cells in that case, okay. So how does it happen? It basically, these are your estrogen receptors, and these, as the name suggests, these bind to estrogen that is present in the environment, and when this binding happens, it triggers a whole set of chemical reactions which amplify the growth potential of a given cell, and that is how breast cancer cells divide much faster as compared to other cells. But now, if you give a drug which is able to bind to this receptor such that the receptor becomes unavailable for estrogen to bind, then what you have done is you have blocked the sensitivity of a cell to growth hormones around, and that is how the hope is that it would curtail, okay. But then of course resistance happens. What are some possible reasons? A, it is possible that not every cell has very high levels of that molecule. It is possible that some cancer cells are very similar to normal cells in terms of how much estrogen receptor is present on the surface. There can be mutations in this molecule such that the drug is not able to bind. The structural changes can happen. Even if the drug binds, talking of adaptability, the cell is able to use other chemical molecules to do the same thing. Right? So there are all these different possible mechanisms. So the question is, can any of them drive metastasis? If yes, then how? So what we did here in this particular case study is, and before I go, I just introduce one more terminology. Now we talked about that in metastasis, when we think about metastasis, most solid tumors are epithelial in nature, which means that they do not move, they do not migrate. Then how do they move? So they are able to gain some of these properties which are called mesenchymal properties, which is the exact opposite. Migrate and invade but do not adhere, and this is called, as you can see, the name suggests, epithelial to mesenchymal transition, or EMT, which allows cancer cells to leave the primary tumor. Now once they reach a distant organ, they no longer need to migrate, they no longer need to invade, they can actually settle down and start growing again, and they undergo the exact opposite transition called MET. So this EMT and MET cycles continue to happen, which is what allows cancer cells to keep moving and then settling down at different organs. So the question we were asking is there a connection between estrogen receptor and EMT? Right? So what we had already figured out, we as in the community, that there are at least two variants of this molecule. This one, estrogen receptor 66, this tamoxifen actually binds to and shuts down the signaling. There is another one which tamoxifen is not able to bind to because of the structural changes, and that is why whenever you see resistance, you see that this molecule is actually higher in those patients to which who do not respond to this drug. Now the next thing that comes is that, okay, they may exist, but do they regulate each other? Is the presence of one somehow governing the presence of the other? Okay. So there is information on that when the level of this molecule is high in a cell, it ensures that the level of another molecule is low, because it's able to bind to specific other molecules which trigger a whole cascade of reactions and make sure that this does not happen. So it is very difficult for these molecules to coexist. Either one will exist or the other will exist. Okay? But this is so far only about estrogen receptor. What about EMT? So the other, so when this is high, this is low, and vice versa. The other information we have is that these two molecules which drive EMT are regulated by this molecule, and the mode of regulation is opposite. So what this molecule does is tries to increase the level of this molecule. That's why it's green. Okay. So when this will be low, this will also be low, because there's not enough acceleration coming in. But this is a boring system. You have just one side flow of information. This controls this controls this, done. One-sided systems are not very interesting to study, right? But then there is a regulation here. This molecule reduces this molecule. Now there's a feedback loop. Okay, what are the different possible scenarios? This is high, this is low, and when this is low, and because this is low, it will not be able to inhibit the other, so it stays high. Right? That's one state of the system. What is the other state of the system? Just flip the arrows. This is low, so there is nothing to inhibit this, so this will go high, this will go high, and this will stay low. Right? Now what are the implications of this? When this is high, cells are sensitive to the drug and cells are not moving because EMT program is low. When this is low, then cells are resistant because the other molecule goes high and they are moving. Right? So there are two states that this system allows. The epithelial cells are sensitive to tamoxifen. The mesenchymal cells are resistant to tamoxifen. So the way the molecules connect to each other itself allows for two cell states to exist. Okay? Now of course each of these papers shown here had studied one of these molecules and one of the interactions. What did we do? We put them together and asked the question, when you put all these interactions together, do you get new properties which you did not get earlier? And the answer is yes. Okay. We did further simulations. This was led by my student Sarthak, and showed that cells could switch back and forth depending on various external parameters in the model. So what the model predicted is that also if you drive EMT, you can drive resistance to tamoxifen and vice versa. Okay. So these were the predictions of the model, which we looked at experimental data where people induced EMT. These are some experiments done in the lab where you measure the levels of these molecules, and you can clearly see that when EMT goes up, estrogen response goes down. So EMT can drive resistance to tamoxifen. So when cells are leaving the primary tumor, they are already drug resistant because these processes are coupled to each other. Vice versa, when you give tamoxifen, what you are doing is you are silencing estrogen receptor. you are bringing down its levels, EMT goes up. So when you're driving resistance, you're already pushing the cells to become more metastatic, right? So this is a system which can be driven in both ways. A appreciates B, B appreciates A. Whether you increase A or you increase B, both of them will happen simultaneously. That's the thing about feedback systems. You don't need it to drive it from one end. You can drive it from either end and reach the same outcome. Okay. So what did the mathematical model tell us? It told us that the occurrence of metastasis in women who had resistance to tamoxifen is not a coincidence. It is occurring because these two processes are so tightly coupled to each other that they can actually drive this. So that was one thing. What is the other thing it told us? That when we expect that tamoxifen will kill every single cell, that's not the only outcome of the model. The other outcome is that it becomes more metastatic, right? So the sensitive one will be killed, but the resistant one will be more. Now, what we do not have right now are numbers. How many cells get killed versus how many become more metastatic. That we do not have. But we know that these are the different outcomes that are possible in the given system. Okay. So it reveals multiple cell states, it explains this clinical observation, and it also suggests that if you give tamoxifen together with molecules that can inhibit EMT, then you are likely to have a better outcome because this is a side effect of the drug. Let's take another short case study. This is melanoma that we already talked about earlier. Now what we know is that melanoma, a large proportion of that contain mutations in a given pathway, and thankfully we have targeted therapy again which is available for this cancer. Okay. So what people have shown, this is again work led by Sarthak and Simadri in the group, is that when you begin to treat the drug, so what this graph shows is they measured the molecules, these two molecules in every single cell in the population. And as you can clearly see that even in presence of the drug, the population structure is changing. You see many more cells which are in this quadrant, but after 10 weeks, the population structure has changed. And when the population structure has changed, the same drug will not work because it is some cells which were sensitive to this. So these cells disappeared, but these new cells came about. These cells which were not there prior to treatment of the drug. So the only explanation is that these cell states were induced by the application of the drug itself. So in this particular system, what you see is that drug treatment itself can give rise to new states, and the drug treatment can change the frequency. So we had this experimental observation and we wanted to see whether mathematics also gives you the same answer. So again, we built up a minimal network similar to the one I showed you earlier, and they showed that this could give rise to multiple cell states. There we saw 2 states, here we saw 4 states. And again, when you look at multiple molecules together, what you see is that prior to the treatment, which is shown in orange here, there is this population here and this another population here. Each dot is a cell in this graph. And after treatment, you have only this population. So this population clearly died, but the other population survived. Okay. But interestingly, when you do 2 drugs together, you begin to see new states which were not seen earlier. So the drug treatment itself is able to push some cells to acquire a different personality which did not exist until you applied that stress. So again, what this is telling us is that yes, you can have different cell states and drug treatment can change the distribution and also give you new states which were not seen earlier. Okay. So what are the lessons we have so far, right? So again, we assume that we have very efficient therapies, which we have as compared to chemotherapy and radiation therapy and surgery. We have come a long way, but still there are some cells which will not die. There are some cells which will survive. How do we identify those cells? How do we minimize those cells? Are the questions which we still have to understand. So what this tells us is that cell death is not the only inevitable output for a targeted therapy. It can actually make cancer stronger by pushing a percentage of cells. Of course, we do not have the exact numbers, I'll say that again, but it is possible, and mathematical models can help in better identifying drug strategies. Now here an argument can be made, why do we need a mathematical model? Let's take all the drugs that we know, let's take different kinds of cancer cells, let's do the experiment and we'll get the answer. Okay. So this experiment was actually done, I'll come to the answer in a paper that appeared 2 years ago. they tried more than 100,000 combinations. So approximately 1200 drugs and of different concentrations and approximately 120 cell lines. Cell lines are basically representative of different cancers belonging to breast, three other, it's just on the next slide, 3 different cancers, 100,000 combinations. And the question they asked was very simple. In what percentage of cases will you see synergy? Synergy is defined as cell death caused by the combination is greater than cell death caused by drug A plus cell death caused by drug B. So what do you think is the answer? How many of you think it was greater than 20%? So out of 100,000 combinations, 20,000 combinations were synergistic. 20%. Okay. 10 to 20%. 5 to 10%. Just synergy, simple. And this is not patients, this is just done in the lab. 1 to 5%. Less than 1%. So the answer was around 5%, it's not as bad. But of course, by the time you go to the patient, that answer will go to less than 1%, because these are just done in the lab, and we can easily cure cancer in the lab. We can easily, well, not easily, but we can to some extent cure cancer in mice, but we are not able to cure cancer in humans. Okay, so there is a rate of attrition that follows with this process as well. So if this is where we are, right, that we can of course try this, and please remember that this is a this is a very high resource experiment. Not every lab in this world will have the resources to do these kinds of experiments, right? So we need mathematical models to come in and improve this 5% to a much higher rate eventually. Okay. Now let's contrast that situation. Let's say that your car brakes worked only in 5% of the cases. And more importantly, you don't even know what that 5% is. That's where we are right now. Okay, just to paint a picture. Okay, then you can ask, why is there so much difference in systems that we have created as humans versus the systems that exist naturally, right? So let's think of this system, which is a reasonably complex system that we trust our lives with, right? Okay, and let's contrast it to some other simple biological system. This is a bacteria, which has probably the same number of feedback loops and so on, but we do not have the design manual. Because we didn't design it, we don't know what connects to what and why it connects there. This is, okay, this system has evolved. We don't even know what stresses has gone under it, but we know this system very well, reasonably well, right? So how do we then understand and fix such? Unless we understand, we can't fix these systems, right? So in the construction industry and aviation, transportation industry and various other industries, there is this concept of a digital twin. What that means is that, whatever the real object is, you will have a virtual replica of that. More importantly, you will keep collecting data, how the real object is doing, and feed that to your virtual model, because you have constructed the system, you know the rules, right? And then you input different perturbations because you are dynamically collecting data, constantly trying to improve the model and trying to predict when this model may fail or when some other catastrophic event may happen, right? So this constant interplay is beginning to play a crucial role in all these engineered systems, and people are beginning to talk about this in the context of cancer as well, right? That can we collect as much dynamic data as possible and improve our models. What I showed you right now are rudimentary models. What's going on within a cell. We didn't talk about what's going on within a tissue. We didn't talk about what's going on when a cancer cell has entered the blood vessel and so on, right? This is a rudimentary model, but these are starting points. This is F is equals to MA or PV is equals to nRT. You use that and then you build upon that by collecting much more data and trying to predict that, right? So also the technology is becoming much more advanced that you can collect dynamic data. You can collect, you can actually, you can just as we have QR codes for each payment, you can put a QR code on each cell now and see whether that cell survived during drug treatment, whether it switched to a different type, so on and so forth, right? So you can collect dynamic data. The technology is advancing. Also in the clinical setup, now more and more cancers, we are doing what is called liquid biopsy. So what is solid biopsy? Solid biopsy is you take a solid tumor, you cut a section of it, and then you analyze it. But liquid biopsy means you just take the blood. And in that blood, is there enough information to tell you whether a cancer is progressing, whether a cancer is slowing down, whether a cancer is responding to the drug or not, right? So those challenges are being met, and liquid biopsy of course is much cheaper, much more convenient to the patient as compared to solid biopsy, and you get more dynamic data. You can't keep cutting slices of a tumor, every 2 to 3 weeks, but you can do that for liquid biopsy, right? So what are the open questions, right? So as I said, we have this data now that not every cell dies. Some cells live, some cells become more aggressive than what they were before. Some cells become dormant for some time, which means they stop dividing and they wait for the drug to be removed and then they start dividing again. Okay. All these different behaviors are possible, but what we do not have are numbers. How many of these cells do that, and how does that depend on the drug, the cancer, etc., etc. So we clearly need to understand more advanced mathematical models. And then the question comes, what do we need to do as a community, right? So we often think about different subjects. Okay, I am a biologist, I am a chemist, I am a physicist, I am an engineer, etc., right? And we sort of silo ourselves in that scenario. So this is from an article I wrote almost 2 years ago, that if cancer cells are using all strategies that they have, they are not saying, well, I am a biologist, I only know how to do this, right? So they have different identities. They are comfortable with identity crisis as an identity because they are changing all the time, right? And they are cooperating with each other in different ways. But we, the collection of 10 to the power 14 cells, are less intelligent than them in some sense, because we have created these artificial silos where we don't talk to each other, where we don't work with each other. So we need to get out of that. We need to, if the cancer cell is doing this, why are we not doing this as a community? Why are we not thinking about this as a complex system and getting feedback from different scenarios to eventually make a better outcome, right? So of course some of that has begun to happen. This is, for instance, National Cancer Institute in the US. They have set up what they call physical science oncology networks for the past at least a decade now, where they are bringing together cancer biologists, physicists, engineers all together to solve challenges in imaging the data, in analysis of the data, and making better digital twins, etc. Even an immunotherapy, which is literally the cutting edge therapy that we have right now, people are beginning to use different kinds of artificial intelligence scenarios. There is a society called Society for Mathematical Biology, which is almost 50 years old now. That has a subgroup called Mathematical Oncology, and I'm fortunate to have the chair of that subgroup sitting right here, my good friend Jason. And also recently ISC, we received funding to set up a center which focuses on computational oncology, and we'll be doing workshops all over the country. It's a capacity building exercise. We'll be doing workshops for undergraduate students, graduate students coming across disciplines to begin to think about cancer as a complex system and then eventually hopefully impact clinical outcomes in the near future. So I'll just end here. In many biology research articles, when they end, what you would often see is a fantastic cartoon, right, which reflects the views as to how these different molecules interact with each other and so on. But if I just give you this cartoon and ask you, tell me which node to hit so that I can kill the cell. Only 100 options. Can you do that just by looking at this cartoon? It's like identifying which wire to cut when you're trying to defuse a bomb. So unless you have domain knowledge, you'll not really be able to do that, and you may have an outcome which is exactly opposite to what you're trying to do. Right? So these cartoons are great because they reflect our understanding of what is there, but these are incomplete because it doesn't help you move to the next stage of being predictive about these things. And that is the information that we need to add to these cartoons to make them more quantitative and more predictive. And you should realize that cancer is a complex dynamic system, and mathematical models sometimes reveal our hidden assumptions, just as we talked about, what are the different assumptions in targeted therapy. And we realized using mathematical models later that assumptions were wrong. Okay. So mathematical models coupled with different kinds of experimental data have steered our understanding of multiple complex systems, and I am of a strong belief that we can do the same for cancer biology as well. Okay. With that, I would like to thank the fantastic team of students and colleagues I have had the fortune to work with, who have been a part of this journey and continue to be a part of this journey across different institutes, across different as well. So please do not think of yourself as a siloed person in a given training. You may have received a given particular training for whatever reasons, but you have the potency to contribute to these open questions in biomedical research. Thank you once again for your attention, and I'll be happy to take questions.
Hello, Professor. I had a question on digital twins. So, your approach is creating a digital profile of a patient. But would you be interested in, like, say, a virtual cell or a virtual cancer cell rather than a whole patient? Because I think that would be a much more bottom-down approach of and try to build from there.
No, that's a very good question, right? What scale do you start with? And so yes, so our approach, in fact, our research group's approach is to build a virtual cell. But there are other experts, broadly speaking, in this field, who are starting from, the other end. And because they see value in that, and I'm not saying I don't see value in that, but whatever they are trying to optimize, say people working with radiation therapy, so they are looking at the images of, say, glioblastoma, brain tumors, and various other scenarios, and they are trying to identify, okay, what was the impact of the radiation on the tumor mass? In which direction did it shrink? In which direction did it not shrink? Right? So again, it depends on the question and scale that we are trying to address. I'm not saying one versus the other. I think one should be integrated with the other, bottom up as well as top down.
Yeah, hello. Thank you for the interesting talk, very interesting aspects you covered. So I had two questions which were kind of related to each other. The first one was actually I saw in the context of antibiotic resistance that in certain scenario, I think it was a report that, what they did was there was antibiotic resistance seen against a particular antibiotic. And then what they did was they completely stopped using that antibiotic. And then, as you said, in evolution, how the survival of the fittest, the cells adapted, and the antibiotic resistance bacteria which were dominant, then they became dominant because there was no survival advantage for that. So, and then you can again, subject the cells to that same drug. So then those antibiotic resistance would die out eventually. So I mean, in the context of cancer, in terms of the plasticity, the example of ER receptor which you showed is something, have something of this been tried? That is the first question. And the related part to that was that you mentioned about plasticity in terms of the ER. So I mean, what I want to ask is there predictability of these plasticities in different people, in different patients, or every patient has a different set of plasticities that evolve differently in them? Because if there is predictability, then you can alter the drug regimen according to that, because you know in what way it is going to turn in the future. So yeah, I want some insight in this regard.
No, those are fantastic questions. In fact, the first one, yes, the answer is yes. People have tried this, what they call adaptive therapy, where the central idea is that let's not kill every single cell, right? So the underlying assumptions here are that there are two types of cells, sensitive and resistant, which are not changing back and forth, but they are competing for resources. So if you deplete every single sensitive cell, then resistant cells, as you rightly pointed out, get the advantage and begin to grow rather fast. So therefore, let's stop the therapy in between, give what they call drug holidays, and that can improve the patient outcome. And the results that I know so far, and Jason can correct me if I'm wrong, is that, I mean, this therapy has this advantage that the drug burden comes down on a patient, right, because you're giving much less drug. And at least in prostate cancer, there are some clinical trials where this seems to be reasonably working. Now, whether it is more efficient than constant, I think those comparisons depend on, because they have been tried on relatively small cohorts, so how universal they are questions which still need to be understood. Coming to the second question, can we predict the rate of plasticity or rate of switching in individual patients? in which directions and all, right? So I don't think we are there yet. Because we would need to collect information on whether the rate of switching from state A to state B, what all different parameters it depend on, and what all different variables it depends on, and how those variables crosstalk with each other. So for instance, and this is something my student Paras who is sitting here is working on, is that say the rate of switching from state A to state B, does it depend on other does it depend on how many state A cells are there already in the population versus how many state B cells are there in the population. So there we have some answers that it is dependent. So it depends on the local density for sure. What other factors it depends on, we are still trying to understand.
You gave the analogy of digital twin when it comes to industries. And now what is being done in this industry, and my question is more targeted towards when it comes to medicine, at least to my knowledge, it is mostly clinical trials. And there is a gap which has to be bridged from the last point, which is the patient which he is himself going through, right, to connect to the research. So if at all we have to even reach to a level of a digital twin, there should be a constant 24/7, not only monitoring but data collection from the pain, from the point of diagnosis until it's cured and until it's cured and wherever he's going to reach, either he's going to die or it's going to be cured. But what kind of effort is happening towards this?
Right. So again, that is an excellent question, and I think it goes back to the first question that, so in scenarios where that data collection is easily available, such as say doing an MRI and collecting the tumor size for patients undergoing say radiation therapy for instance, there people are building this information into predictive models to see what kind of therapy should be now given, should the dose be adjusted or so on and so forth. When it comes down to the level of cell, we still do not have clear understanding of how to collect the data. When let's say you pull a tumor out of someone's body and you grow it in mice, the mice environment has already changed the tumor, right? So that is why we are able to cure things in mice but not in humans, right? So that's the major issue, that you have placed the system in an artificial setting, but you want the result for a real setting, right? So there is a flaw but anyway, that's where the technology is. So we'll have to of course take some steps towards that. So at the organ level, I would say the digital twin concept is being more easily integrable into the pipeline at this stage, but the hope is that at a subcellular or cellular or tissue level, we can develop more technologies which can allow us better monitoring, and we can develop more efficient mathematical models such that we can match the variables that we are collecting. So we still have some way to go there, but it's working at the organ level. Absolutely, yes. So right. So I think at an organ level, the technologies are there to measure the tumor size, orientation, etc. So that can be done. And there again, the dynamic models that are written there do not include in most cases these molecules. They are, the variables are tumor size, tumor margin, number of tumor volume, etc. So it's a much more phenomenological model or much more coarse-grained model in that sense. But as long as it's helpful to the clinic, let's do it.
Yeah. The question I had was, why do some animals such as blue whales get cancers less frequently than other animals like humans?
That's a very good question. I am not an expert on the subject, but what literature I know is that there are levels of these so-called different tumor suppressor genes. One of the famous ones is called P53. Why is it called P53? I don't know. But the levels or the copies of these molecules actually controls the extent to which tumor initiation is possible and tumor initiation is fast. One other question which at least I have had for a long time is, at least I have not heard of heart tumors. Why does your heart not get tumor? Like, are there reasons behind it? So even within the body we have questions to ask as to why certain organs are more likely to get tumors as compared to others. But I don't think we have a very clear answers for that. And again, as far as the evolutionary questions such as the one you asked is concerned, we can only give associative answers. You can't take a blue whale, change its genome and then wait for thousands of years to see whether it was a causative connection or not. So that argument will always remain at a correlative level.
Thank you. So in the example where you gave about the 3 cell states and you have targeted therapy for each of them, and we concluded that even if you do such an experiment, it goes to a new kind of cell state. Now, let's say we have these 3 cell state targeted therapy, and we already know in advance by some simulations, let's say, that what is the cell state it's going to go to given these 3 target therapies, and we have a protein engineer who's developed specific ligands for that new cell state. Now, if you start the whole experiment with the population of these 3 cell states, and you give these 4 targeted therapies, do we expect it to go to a new 5th kind of cell state, or?
Yeah, so the probability is not 0, but what that probability is, we'll have to do the experiment and figure out. So I'm not saying it's not possible or saying that because you use mathematical models, that probability suddenly went to 0. No, all I'm saying is models can be used to better characterize the dynamics that we have, and it reveals the underlying assumptions that we have. The underlying assumptions is that every cell is destined to die. That is not happening. Clearly there are other things happening. How do we leverage this information to come up with better therapies is the next set of questions which when I say give 2 drugs, should we give them together? Should we give them one A after B after A? Should we give drug holidays? So those are questions which we hope that mathematical models can help narrow down the set of possibilities which can then be tried out.
Mohit, we have a few questions from YouTube live stream. One, Raghav is asking, what is cancer metabolism?
So cancer metabolism, from what I understand, is how cancer cells are utilizing different resources to gain energy, right? So cancer cells are dividing much faster, so they have different metabolic needs as compared to cells which are the normal cells are. So there is literature on cancer cells doing their metabolism differently than the normal cells. This is called Warburg effect and has been extensively studied.
Right. Somov is asking, can cancer cells cooperate with non-cancerous cells?
Whatever literature I have seen is more of competition, that non-cancer cells seem to cooperate and try to eliminate the cancer cells, but only in initial phases of cancer development. I'm not sure if the later stage of cancer development these kinds of studies have been done.
Right. A couple of more questions. Sejal is asking, there is work going on at artificially recreating the entire organ in labs, the heart for instance. Is that not a more efficient methodology compared to digital twins if we can really crack it?
I think we need both of them because because for digital twin you need to match it with reality, otherwise it will remain digital, right? So if you want to inform reality, you'll have to compare it with reality. So we will need both the experimental technologies to go to the stage and digital numerical simulations to be able to handle that level of simulations so that we can eventually compare them.
Right. And one more from Arpit. He's asking, I work in an acute leukemia lab, blood cancer. So how do mathematical models fits in this scenario, since standard EMT process does not occur here?
Yeah, absolutely. So the concept of cell state transitions, although not called EMT, has been seen in leukemias as well, that they are able to switch to a different behavior. I don't work in liquid tumors, so I don't know the exact terminology being used, but this concept is there as well. The concept of dormancy, which we talked about in metastatic scenarios, those are all present. So these ideas, with of course obvious contextualization changes, can be applied there too.
Right. We have more time for more questions from here.
I think, yeah.
Thank you. Excellent talk.
Thank you.
Just wanted to ask, I see a list of subjects here, and what I see is evolution to be the underlying thing for many of these adaptations, including cancer,
yes.
This thing. So, are there actually groups or things which are specialized looking at evolution and studying from that perspective? Because you normally don't hear specialized groups or universities or things looking at evolutionary studies.
Right. Thank you for pointing that out. I should update this slide because the first ecology and evolutionary biology PhD student who has joined our group as a postdoc is just starting next week. So I should update that. And also my friend Jason sitting here, he thinks about evolutionary therapies in the context of tumor immune interactions. So because tumor cells have the ability to trick the immune system and tell them, look, I am not tumor. and also change their behavior that, well, you have lost the ability to identify me as tumor. So they are literally ecosystem engineers in that sense. And then immune cells also have this plasticity. Some are more efficient versus some are less efficient, which again, it depends on the environment. So he is studying that from that perspective, looking at molecular aspects of what it takes a tumor cell to be identified by an immune cell, and then again looking, sort of zooming out and looking at how that interaction dynamics will impact the efficiency of immunotherapy, which is what he's trying to improve. So certainly please talk to him about more of that.
We have one more question from Bhanu Prakash. He's asking, can you elaborate on the mathematical models you have used? Are they data-based machine learning models or any other specific models?
So the mathematical models we have used is, in the examples that I showed, is a set of coupled ordinary differential equations, where each differential equation is basically the concentration of each of the molecules that I talked about, which is dependent on other molecules. So these are coupled ODEs, and they have some production and death rates.
Yes.
Yeah, so how do you define the stage? I mean, in what stage the cancer, to say how the cell multiplication, right?
Mm-hmm.
So how do you define, this is the first stage, second stage, third stage, and the final stage?
Mm-hmm.
So how does we come to that conclusion?
So that is a clinical decision. So I think clinically, and again, Jason is a doctor also, so he can correct me. So clinically, there are stage and grade. These are the two metrics which are used. I get confused on which is which, but one of them depends on whether the cancer is present only, when we talk about solid tumors, is present localized, or is it already moved to the lymph nodes, or is already metastasized. This is called T&M staging, where M stands for number of metastatic nodules, N stands for number of lymph nodes, and T stands for tumor site. So there are these different pathologists who do this in a much more rigorous way, in that sense. This information is not based at a cellular level, this is based at an organ level.
Any more questions? Okay, if not, please thank Professor Mohit Kumar Jolly for this wonderful talk and taking so many questions.